If you remember back at the beginning of the class, we talked about some situations where the fact that computers have to round numbers to a finite number of digits could lead to some significant calculation errors. So, to see why that's an issue with Gaussian elimination and our new algorithm, take a look at this system and assume, yes, somewhat artificially, that our operating system rounds every number to 4 digits. We could do a more realistic example, but then we're doing 20 decimal digits and it gets messy, right? If rounding to 4 digits will be enough to illustrate uh, what the area of concern is here. So first, you can quickly confirm that the exact solution is 1.01 comma 10. Okay, now keep that in mind. And using our Gaussian elimination procedure, our first multiplier will be A11 divided by A12, which comes out to 2,550. Now, if we multiply every element of row 1 by this amount, round those results to 4 digits, and subtract them from row 2, we get this matrix. And we can start the backward substitution process. Solving the last row for x2 gives us x2 equals 1.009, which has some round off error, but not a significant amount. Okay, the trouble really starts when we solve for x1. Solving this equation for that value, and again, rounding to 4 digits at every step of the process, gives us x1 equals 26.67, which is significantly off from the actual value of 10. Okay, so what happened? Right, the problem actually started here. The significant difference in magnitude between the two values, with the smaller number specifically being in the denominator, resulted in a really large multiplier. And when this value got multiplied by other relatively large numbers, like the 2, like the 2 in the 46 range, the result was even larger numbers that lost significant precision due to the rounding. Okay. Um, in practice, is this a common occurrence? Well, no, but it does happen, and it is a particular concern with this Gaussian elimination algorithm because we're potentially doing these with large matrices, 100 plus rows and columns, and there's a lot of multiplication, there's a lot of division and subtraction. So there's a lot of potential for this kind of weird special case situation to show up. And the heart of the problem is that there's really no way to predict in advance when that's going to happen. So what we want to do is we want to come up with a preemptive strategy, something that we can implement in every case that will reduce the likelihood of this kind of situation occurring. So let's take a look at one option here. So these strategies that we're going to look at, they're all called pivoting strategies because they're all based around trying to get a number into the pivot position. Remember, that's ultimately the number on the main diagonal that goes in the denominator of our multipliers. Uh, that isn't going to cause a potential problem. Okay, so our solution here with this method called partial pivoting is going to be to pre-scan the column being processed at every step, and we're going to move the row with the largest value in that column into the pivot position. For example, with my example here, that means reversing the two rows. So now we're pivoting on that 7.65, which obviously is significantly larger than the 0.003. Now, if we repeat those calculations, our multiplier is now 0.000392, again, rounded to 4 digits, and much smaller, right? Much smaller. Now, if we apply the elimination algorithm, eliminating the 0 in the A21 position, we get this matrix, and ultimately we're going to get some better results. If we solve the second row for x2, we get the exact answer that we needed. Now we're going to take that value, we're going to do the back substitution. I'm going to put that into the equation that we get from the first row, and yeah, we get a much better number, right? Much better result. An exact result, right? That's the exact value. Okay, so let's see if we can summarize this, right, and kind of rephrase our algorithm with this strategy in mind. So nothing we talked about on the last slide affected the backward substitution part of the algorithm. So I've just got the elimination section here because that's the part we're going to make a change to. So the area that I've highlighted here, if you remember in the original algorithm, this was the section where we checked to make sure the number in the pivot position wasn't 0. And if it was, we scan through every row below it looking for a non-zero value and move that row up. Okay, well now I've replaced that with our partial pivoting strategy. So what we're doing now is we're doing that same loop. We're going through every row below the pivot position. And I'm looking for the row that has the biggest value in absolute value. So the one that actually has the biggest magnitude. And that's the one that I now switch up into the current row. And again, we do make that last check. If everybody is 0, then the system is inconsistent. And again, we return that there is no solution. So while this partial pivoting algorithm is a good first step, it doesn't completely solve the problem, right? And to see this, take this matrix here. All I did was I took the matrix from my very first example, multiply the top row by 10,000. Right? And doing that gave me this matrix, and I encourage you to walk through the process, do the calculations here. If you do, first you'll see that no pivoting is required because 30 is greater than 7.65. But if you leave it as it is and you go through the algorithm, once again, we get an unacceptably incorrect result. So my solution to this is something called scaled partial pivoting. And all I'm going to do is I'm going to make a little adjustment to how I decide whether or not to switch some rows around. Okay, so the first step is to find a scaling factor for each row. And that value is just the biggest number in the row. Okay, so for the first row, that would be the 464,900 figure. And for the second row, that would be 71.45. Okay, so now I'm going to take the numbers in the first column, the column that I'm processing, and I'm going to divide each one by its scaling factor. So for the first row, that's 30 divided by 464,900, which gives me that really small decimal. And for the second row, I get 7.64 divided by 71.45, which is a bigger decimal. So now to make my decision whether or not I'm going to switch rows, instead of looking at the actual cell values, I'm going to look at these scaled values. So because 0.1069 is the biggest scaled number, that's the row that I actually want to pivot on. So I'm going to make the switch. I'm going to move that 7.65 row up into the pivot row position. And again, I don't want to bore you with a bunch of arithmetic calculations, but I do encourage you to walk through them on your own. And if you do, you should see that this method does result in the exact solution. Okay, so I've got our revised algorithm here. This is what we're going to call Gaussian elimination with scaled partial pivoting. And I've really made two changes. First, I've added this section here. We're going to need the scaling factor, that biggest value from each row over and over again as we process all the rows of the matrix. So instead of looping through the columns, looping through each row repeatedly at every step through that second loop, we just do it up front. Loop through every row, find its maximum value, store that in this S sub I value. That adds an additional n squared operations to the algorithm, which is still less than the n cubed we calculated previously. So this isn't going to significantly impact the runtime. Then the second modification is, again, to this section where we determine whether or not we're going to switch some rows around. And all I've done is, instead of looking at the cell values that are in the column, I've looked at the cell values divided by the scaling factor. Right? And then we make the exact same decision. The biggest one is the one that we want to move into the pivot position. And that's it. Those are the only changes. So now we've got two more algorithms in our toolbox, and as before, I encourage you to take time to try to implement these right? You'll really get to know them a lot better if you take the time to write out some code. Now, as I mentioned previously, this Gaussian elimination runs in big O of n cubed time, which is good but not great. There are some other methods that do get better time. So that's where we're going to go next. We're actually going to talk about something called factorization. We're going to look at how to factor a matrix into the so-called LU form, lower and upper. And then we'll see how we can use that to improve the runtime of this process of solving a linear system of equations.